Imagine you hire like a brilliant new intern,
Okay.
and this kid has flawlessly memorized every coding textbook ever written. I mean, they type at lightning speed, they never sleep, but there's a huge catch.
Let me guess. No common sense.
Exactly, zero common sense. They have absolutely no idea what your company actually does. And that is exactly what it feels like relying on AI to write your software right now in 2026.
Yeah, that is a perfect way to put it.
Welcome to today's deep dive. Whether you are prepping for a major tech meeting, trying to catch up on where the engineering industry is heading, or, you're just insanely curious about how the world works behind the screens, this conversation is tailored entirely for you.
It really is a completely new era of engineering, and the skills you need to survive it, they're shifting dramatically.
Right.
We're moving away from simply asking the AI to build
Yeah.
things, and we're moving toward the much harder job of proving that the things it built won't just, collapse.
Won't completely fall apart on day one. So today's mission is all about trust, logic, and validation. We are drawing from a really fascinating presentation by a developer known as at Luck036. The document is titled Validation in AI Era.pdf.
And we should clarify, this isn't just for software developers.
No, not at all.
If you rely on AI to do, well, any kind of complex logical work in your day-to-day life, you are going to want to hear this.
Okay, let's unpack this because the core problem here is well, when this incredibly fast textbook memorizing AI writes code for us, it creates this very dangerous illusion.
The illusion of reasonableness.
Yes. Because the code it spits out usually looks perfectly fine. I mean, it compiles without errors, the formatting is beautiful, and it just feels entirely reasonable.
And that feeling of reasonableness is like the ultimate psychological trap.
How so?
Well, from a human perspective, when you look at a structure that appears pristine, your intuition immediately assumes it's fundamentally sound. Your risk perception just plummets.
So you let your guard down.
Exactly. You start projecting human reasoning onto a machine that doesn't actually possess the capacity to reason.
I think that's the part that really trips people up. Because it sounds so much like us, we assume it's thinking like us, but under the hood, it's really just playing the world's most complex game of autocomplete.
Right. It's a probabilistic prediction model.
It looks at the massive ocean of training data it ingested, and it just stitches together syntactical patterns. It entirely lacks a true internal concept of causality or real world intention.
Which leads to some truly spectacular failures that human intuition just isn't equipped to catch.
Yeah.
If you look at the underlying mechanics of these AI failures outlined in the presentation, they usually fall into a few distinct traps. The first is a lack of logical self-consistency.
Meaning what exactly?
Well, the AI might write a beautifully elegant function, but it leaves a hidden logical gap that completely breaks when the system is actually put under strain.
Oh, wow. And the second trap is the one that really scares me, and that's the total disconnection from business semantics. Like, the code could be mathematically flawless, but completely ignore the specific rules of your industry. I mean, think about a banking application.
Okay.
An AI might write a function that correctly calculates that negative 500 plus 500 equals 0. Mathematically, that is completely sound.
Sure. Basic math.
But in a business context, allowing a negative transfer in a user's account might open the door to money laundering or, outright theft.
Because the AI doesn't know what a bank is.
Right. It just knows math.
And because it lacks that context, we hit the third trap, which is hidden security and compliance risks.
The intern strikes again.
Exactly. This overconfident AI intern might pull in unverified external code libraries
Yep.
or leave massive data privacy loopholes simply because it doesn't comprehend the real-world legal consequences of a data breach.
It doesn't care if your company gets sued.
It literally cannot care.
So, think about the last time you blindly accepted a big block of AI generated text or code. If our human intuition is being actively tricked by how clean and professional the output looks, we need a new defense mechanism. We just can't eyeball this stuff anymore.
No, intuition has to be completely replaced by automated, full process validation. You need rigid systems that mathematically and logically force the AI to prove its work.
Prove its work, like in grade school math class.
Exactly like that. But to build that kind of fortress, you have to adopt some unbreakable rules for your workflow.
Okay, so let's get into those rules. The first big maxim we pull from this research is incredibly definitive. The slide literally says, if you can't validate, don't change.
It sounds simple, but in practice, that is a massive hurdle for teams.
Yeah.
It means that if you do not have a verifiable way to ensure the absolute correctness of an AI's proposed change, you reject it.
Mm.
Period. It doesn't matter how intuitively obvious the improvement seems to be.
Right. Let's ground that in a real engineering scenario from the document. Take a GCD algorithm, the math used to find the greatest common divisor between numbers.
It's like a very standard function.
So a developer might be looking at an older recursive version of this code. And a recursive function is one that calls itself over and over to solve a problem. It looks very elegant, but it can eat up a lot of system memory because every time it calls itself, it stacks up another layer of memory.
And then the AI comes along and says, hey, I rewrote this using an iterative loop instead.
Right. And iterative loops generally use less memory and run faster. So any seasoned developer's gut reaction would be to say, awesome, iterative is better, let's merge that into the project.
Yeah, but under the new rules of the AI era, that gut reaction is dangerous. You cannot assume the iterative code is better or even functional just because the AI says so.
So what do?
You have to use actionable proof. You run benchmark tests, you use performance profiling tools, and you quantify the exact execution time and resource consumption.
You want hard numbers.
Exactly. You only accept the AI's modification based on reproducible, hard data.
That shifts the burden of proof entirely. Now, here is a rule that genuinely made me stop and rethink how I approach troubleshooting. The author presents this as the absolute non-negotiable golden rule of code validation.
It's a big one.
Yeah. Either modify source code or our unit tests. Never both at the same time.
Yes.
At first glance, that feels kind of counterintuitive. I mean, wait. If I ask the AI to completely reread a function to make it better, shouldn't I also update the tests so they match the new code?
It's tempting, but no. Changing both at the same time is like, it's like changing the lock on your front door and getting the new key cut simultaneously
Yeah.
without ever testing either against the original door frame.
Oh, wow.
You have absolutely no idea if they actually secure the house anymore. You just
Hmm.
know that your new key fits your new lock.
That is a perfect way to visualize it. When an API agreement or a core function is adjusted by the AI, your existing test baseline is your only anchor to reality. The goal is to maintain strict numerical stability in your tests. You keep the numerical values and the expected outcomes exactly the same as they were before the AI touched anything.
That old test acts as a tripwire.
Right.
If the AI rewrites the code to make it faster, and suddenly the old test fails, that failure explicitly reveals exactly where and how the AI broke the system's core logic.
It forces the AI to conform to the established reality of your business.
Right, rather than letting the AI redefine reality just to make its own new code pass.
I'm trying to picture how I'd actually use this in a fast-moving daily workflow because, if I'm managing thousands of files, I can't be doing this manually. I would need to automate the fix but keep a hard stop before anything gets published or delivered to a client.
There is a very pragmatic workflow to handle exactly that, and the document refers to it as the fix then validate loop.
Okay.
To see it in action, think about managing massive amounts of subtitle formatting.
Like SRT files for video production.
Exactly. Subtitles require incredibly strict formatting and perfect time codes, or the whole video is just ruined.
So step 1 is the source. You identify the raw text or the subtitle file that needs work and establish your target requirements.
Then step 2 is modify. This is where you let the AI edit, adjust, or refactor the content based on those needs.
Just let the AI do its thing.
Right. Then comes step 3, the automated fix. You might run a script, let's call it /fix strt.
Right.
This handles the mechanical standardization, ensuring the time codes align and the text breaks properly.
Got it.
But step 4 is the critical checkpoint. That's /validate cert.
So you run a validation program to verify the content completeness and the internal logic, and this creates a closed loop.
A completely closed
If
loop.
it passes validation, it is delivered, done. But if it fails, you don't just manually tweak it to force it through. You investigate the root cause and you loop back to step 2, the modify stage.
And you never, ever skip the validation step to go straight to delivery. The core principle is always fix first, validate second, operating strictly as a closed loop. It just removes the temptation to push things to production because you're running late.
And that makes total sense for text formatting or subtitles, where the rules are pretty static. But if I apply that to massive, complex data pipelines or like hardcore mathematical transformations, A simple checklist and a format validation script aren't going to cut it.
No, they won't.
The AI could be introducing subtle data corruption that a basic format check would completely miss.
That gets to the heart of the issue,
Yeah.
and it requires bringing in the heavy artillery. To keep AI in check on complex systems, you need advanced mathematical strategies. And the first of these is round-trip testing.
The boomerang effect. I love the logic behind this.
What's fascinating here is the elegance of round-trip testing. It lies in its simplicity. You take an input value, let's call it X.
Okay, X.
You apply a forward transformation function to it. Maybe you are encoding it, compressing it, or encrypting it. We'll call that transformation T.
So now X has been fundamentally changed into something else. It's T of X.
Exactly. Then step 2, you apply the exact inverse transformation function, mathematically denoted as T, to the negative one.
And step 3 is where the AI proves its worth. The final output must perfectly exactly match the original starting input X. The inverse of the transformation of X must equal X.
Exactly.
It's like taking a highly sensitive legal contract in English, having the AI translate it into French, and then having the AI translate that French version back into English.
Yes, perfect analogy.
If the final English document has even slightly different legal obligations than the original one you started with, the AI hallucinated or messed up the translation somewhere in the middle.
Round-trip testing is the ultimate litmus test for data integrity. If the boomerang doesn't come back to the exact same spot, your system is broken.
Right.
And this is used everywhere in complex engineering. Data encoding is the classic use case. You decode what you just encoded, and it must equal the original X. It's the only way to prove there was no data loss or precision loss.
And the document shows this applies to hardcore math operations too, like inverse spectral factorization.
Yeah, that sounds incredibly intimidating.
It does, but the concept is brilliant. It basically means if you break a signal or a sound wave down into its base frequencies and then reassemble it, you better get the exact same wave back.
Or consider base conversions. Computers often convert numbers from our standard decimal system into specialized formats like CSD or canonical sign digit.
Right, which allows computer microchips to perform addition and subtraction much faster.
It uses fewer non-zero digits. But if an AI writes a function to convert decimal to CSD to speed up your processor, you have to test it by converting it back to decimal. If a 10 goes in and an 11 comes back out, the AI's optimization just broke your core math.
Even basic arithmetic identity has to be tested, like the rule that P plus V minus V equals P.
It seems so obvious to a human.
It does, but when an AI is writing millions of lines of code, you have to rigorously test even the most basic assumptions to catch hidden floating point errors or, precision drift.
The advantage we have in the AI era is that AI systems are actually quite good at generating both the forward and the inverse code. The round-trip test rigorously checks if those two directions are truly mathematically inverses of each other.
I can see how round-trip testing is an absolute lifesaver for data that flows back and forth. But what if a function is a one-way street? What if you aren't just transforming data, but you're asking the AI to solve a complex optimization problem or determine a logistical route? You can't really reverse a delivery route back into a list of unsorted addresses. How do we test the AI's understanding of abstract rules?
That requires a completely different approach.
Yeah.
And that brings us to the second heavy-duty weapon, property-based testing.
Here's where it gets really interesting, because property-based testing completely flips how we think about quality assurance.
It really does.
Traditional unit tests are highly specific. They say, if I input the number 2 and the number 2, the output should be 4. But property-based testing doesn't care about specific inputs and outputs.
No, it tests the invariant.
The invariants.
Yes. These are the abstract laws of the universe that the code must always follow, no matter what kind of data you throw at it. Instead of a human manually writing 5 or 10 well-thought-out test cases, you feed the system thousands or even millions of randomly generated, bizarre edge case inputs.
And this technique is known as fuzzing.
Fuzzing, exactly. You are testing to see if the abstract rule holds up under absolute chaos.
Let's explore what these invariants actually look like in practice, because this is where the math becomes a shield against AI hallucinations. The first category in the presentation is algebraic properties.
Right, the fundamental pillars of logical consistency.
Things you learned in middle school math but applied to enterprise code, like reflexivity, x equals x, commutativity, x times y must equal y times x.
And associativity, where the position of the parentheses shouldn't change the outcome of a chain of addition or multiplication.
Which seemed too simple to worry about.
They do. But if an AI writes a custom data processing engine for your company and it subtly violates the commutative property. During a massive data merge, your whole system's math is secretly rotting from the inside.
And a traditional test might never catch it.
Exactly.
The second category makes this highly visual. Geometric properties. Take the convex hull area property.
Yeah, this is a great one.
The rule here is that for any set of points, the area of its convex hull must always be greater than or equal to the area of the original shape those points made.
So how would you visualize that?
Imagine taking a handful of pins, sticking them into a cork board in a random shape, and then stretching a rubber band around all the outermost pins. The area inside that rubber band must always be bigger than or equal to the area of the pins themselves.
It's a foundational metric for anything involving spatial data or rendering. Another vital geometric invariant is partition conservation.
Right.
If an AI writes a program that slices a complex digital polygon into smaller pieces, the sum of the area of all those cut pieces must strictly equal the area of the original whole.
Matter cannot be created or destroyed, even in AI geometry.
Exactly.
And then we get to graph constraints, which apply to networks, logistics, and routing. Think about how much we rely on AI to optimize delivery networks or internet traffic. A major rule here involves operations like max cut and odd cycle cover.
Right.
No matter what crazy tangled network graph you input into the AI, the result of those specific operations must always produce a bipartite graph.
And to put that simply, a bipartite graph is a network separated into two distinct sets or teams.
Like sports teams.
Exactly. Where no nodes within the same team ever connect to each other. They only connect across the aisle. If the AI spits out a solution where two nodes on the same team are linked, the fundamental property of the operation has failed.
The holy grail of this is the traveling salesman problem, or TSP.
Oh, TSP is legendary.
If you ask an AI to solve a massive traveling salesman routing problem, find the most efficient route across hundreds of cities, you might not have the computing power to easily verify if the AI found the absolute shortest route.
Right, because that takes immense processing power.
But property-based testing offers a shortcut. It says, I don't care if it's the absolute shortest route yet. I just need to verify that the output is a valid Hamiltonian cycle.
Meaning the route must visit every single node or city exactly one time and return to the starting point.
Exactly.
If the AI spits out a route that visits Chicago twice or misses Denver entirely, it failed the fundamental property of the problem. Verifying a Hamiltonian cycle is computationally cheap and fast, whereas finding the perfect TSP solution is computationally massive.
Okay, but I have to push back on the efficiency of this, though.
Okay.
Throwing millions of random fuzzed inputs at a piece of code sounds incredibly resource intensive. Wouldn't it be much more efficient to have a smart human engineer just sit down and write 5 really well thought out, targeted test cases based on their experience?
It sounds counterintuitive, but human experience is actually a liability here.
Really? Why?
What is critical to understand about AI is that it doesn't make human mistakes. It makes bizarre, unpredictable, alien mistakes. It will fail on edge cases that a human brain would literally never think to test for.
Right, because a human engineer isn't going to sit there and think, I wonder what happens if the input is a -0 wrapped in a text string encoded in base 64 and sent backward.
Exactly. But the AI might completely crash if it sees that. Fuzzing uncovers those hidden blind spots. And developers don't have to build these fuzzing engines from scratch.
No, there are libraries for this.
There are powerful libraries that automate this chaos. Python has a library called Hypothesis. Rust uses PropTest, and C++ uses RapidCheck. They auto-generate the madness for you, testing the boundaries of your AI's logic while you sleep.
So if you are managing a massive project, you now have these two conceptual weapons. Round-trip testing for specific data flows, making sure the boomerang comes back perfectly, and property-based testing for enforcing the abstract laws of the universe under a barrage of random data. How does a team actually synthesize this into a daily workflow?
Well, the ultimate battle plan for the AI era comes down to a strict 3-step strategy from the source material. Step 1 is generate and review.
Okay.
The AI writes the initial code, but an engineer must step in for a quick manual review. You use your human intuition here not to approve it, but simply to filter out the obvious, glaring logic gaps or security blunders before you waste expensive computing power running tests on it.
Got it. Step 2 is rigorous testing. This is where you deploy the dual wielding strategy we just discussed. You use round-trip tests to guarantee your data conversions are reversible and safe, and you use property-based tests to bombard the core logic boundaries.
They complement each other perfectly. One protects the specific journey of the data, And the other protects the abstract rules of the system.
And finally, step 3 is validate and iterate. If the code survives that absolute gauntlet, you accept it. If it fails, you don't just manually patch the code yourself.
Ever.
You investigate the failure, you identify the root cause, and you feed that specific context back into the AI to regenerate the code. You loop back to the beginning.
The reality is that this 3-step strategy is not a 100% absolute guarantee of safety. Nothing in software engineering ever is.
True.
But right now, it is the most pragmatic, highly efficient way to balance the sheer overwhelming speed of AI generation with the non-negotiable need for enterprise quality and safety.
The key takeaway is a fundamental shift in mindset. If you are interacting with these systems, you are no longer just a creator of code or content. You are a validator of logic.
That's beautifully said.
Well, we have covered a lot of ground today. We started by realizing that we can no longer trust our eyes when we look at beautifully formatted AI code. We have to shatter that illusion of reasonableness.
Right.
We explored the strict discipline of building an automated math-backed fortress anchored by the rule that if you can't validate it, you don't change it. And we saw how round-trip tests and property-based fuzzing force the AI to mathematically prove its work before it ever touches a live server. Make sure you apply that critical lens to your own workflows this week. But before we wrap up, I want to leave you with one final, slightly provocative thought to mull over on your own.
Oh, the implications of all this are definitely worth pondering.
We mentioned earlier that AI systems are entirely capable of generating. Both sides of the equation.
Right.
But think about what that actually means in practice. What happens if the AI writes a completely flawed, broken encoding function, and then writes an equally flawed decoding function that just happens to perfectly cancel out its first mistake?
Oh, well. Mathematically, the inverse of the transformation would still appear to equal the original input.
Exactly. The round-trip test would pass with flying colors. It would look like a perfectly functioning, rigorously validated system, all while hiding a fundamentally broken architecture underneath. As we move deeper into this AI era, if the AI is writing our software, and the AI is also writing the automated tests that validate that software.
Who is watching the Watchmen?
Exactly. Who is watching the Watchmen? We might just be building a brand new, highly automated bridge out of painted cardboard. Something to think about. Thanks for joining us on this deep dive.